All right. Hi, FanFest.
Hey!
I think I need the machine. Yay. Hi, I'm FC. Starting well. I am FC Idlewise, lead gameplay engineer in EVE Online. And on stage with me today, Ryan Brinkman, VP and Research Director at Dotmatics, Attila Sandner, CEO of Massive Multiplayer Online Science, and Alex Buchev, Research and Development at McGill University. And we are here today to celebrate the 10-year anniversary of Project Discovery. Here's a big number. Over 1 billion classifications have been submitted these 10 years. Yes, 1 billion. This is the equivalent to almost 500 years of non-stop science grind. But it all started in 2016. Your first task was to map protein locations within human cells. Exciting as that sounded, we thought maybe a few of you would try. But in the first month, you delivered over 5 million classifications. Then the second iteration of Project Discovery was to search for exoplanets. You reviewed light data and then flagged candidates for exoplanets that we would then send to astronomers for verification. Then COVID hit. So you analyzed flow cytometry samples for COVID research. Oops. Yeah. Then 2 years ago, we switched the samples from COVID to cancer. So today, EVE Online players are participating in the research to cure cancer. And we have some insights that we wanted to share. Half of all Project Discovery happens in the Forge. In Jita 4.4 alone, 169,000 of you are doing Project Discovery between trades. But then, about 10,000 of you are apparently doing cancer research in 1DQ1 between Titan drops and soft fights. Well, I guess this is EVE. But behold, here are the top 10 most prolific capsuleers in Project Discovery from among you that are in FanFest. Here they are. Please. You are our Project Discovery legends, so congratulations. Any of you here today? Woo! Nice. Happy 10-year anniversary. Please come by our Project Discovery booth tomorrow, because we have some loot for you. And if you're in the top 3, we have special rewards. Nice. Yeah, please, everybody, give a round of applause. Amazing PowerPoint skills. But all of you, you haven't just submitted classifications. You've helped us build Project Discovery. Every bug report, every forum post, every this scoring feels off. Thank you. By the way, we recently updated the scoring algorithm thanks to your feedback, and we keep iterating. So thank you, everyone, for these 10 years. And over to Attila.
So in 2023, we gave a talk, and that was the 20th anniversary of EVE Online. We announced that we are going to release a Project Discovery mobile app in 2024. Now, probably you've noticed that we are a bit behind schedule. But I have good news. We have finally here a working prototype at Fanfest on actual mobile devices, so you can come to the booth and try it for yourself. It's not that we don't have still some technical details to sort out, mostly of how we connect the two worlds, but I feel that Project Discovery is well within our reach on the mobile platform. So when we're talking about the mobile platform, Project Discovery will be part of an app that we call Play Science App. And this we plan to be a hub for different citizen science activities. First and foremost, Project Discovery. But then later on, we'll implement more and more scientific collaborations and more collaborations with the gaming industry. So as a hub app, we are providing some common framework, like the lab interface, which we will use for science communication, dissemination of results. We'll have some social features. We'll have an activity feed. And then we'll have a sort of a marketplace where you can use your analysis tokens that you get inside the mobile app and exchange it for in-game goods. And then some settings and profile. That's not yet ready. We'll have a couple of general features that we'll support. So we'll have dark and light mode support. We'll have multiple languages. In the prototype app, you will see that we have English, French, and Hungarian. This is not representative of the final set of languages. Is that what I had easy access to? And then, of course, we are planning to support different screen sizes and orientations. So it will work on mobile phones and tablets equally well. Now, diving more in detail into the Project Discovery experience. So when we announced it in 2023, I think I said that we want to have a faithful replica of what we have inside EVE Online. And that turned to be not possible very quickly, and for different reasons. So two main reasons. One is the screen estate. So whereas in the desktop app, or in the desktop EVE Online version, we have a rather large minimal screen size that we can count on. That's not true for the mobile, especially mobile phones. So we had to remove all things which are not absolutely necessary for doing this clustering work. The other thing is the pointer device that you're using. So on the desktop, you use the mouse, which is super precise, so you can decide almost to the pixel level where you want to click. That's not true with your finger, where you have an idea of where it's going to touch the screen, but it's nearly not as precise. And the other thing is that whereas the mouse pointer is almost invisible, so it doesn't block really the actual material that we work with, your finger is quite huge compared to the small screen, and it really blocks out part of the image that you have to work with. So we had to really think how we go about that. First of all, we removed everything from the screen. So what you will have is just the image that you work on, of course, the density curves. And if you disregard those two icons in the corner, which are really more about the workflow, like you can go back to the previous screen or submit the result and go to the next screen, you have one control, which are two buttons right now, but that works as a toggle button that switches from clustering mode and to panning and zooming. And the other big change that we did is that we, instead of drawing polygons around the clusters, we said that we'll work with segmentation lines. And that works for two things, because of two things, is that the data is such that all clusters can be separated along a straight line. So it's never the case that you have a jagged, concave polygon to separate two clusters, but it's always a straight line. And the other thing is that, well, I knew because of the scoring, how the scoring works, is that we don't penalize if you are marking extra areas where there is no dots or no clusters. And then, of course, Ryan confirmed that actually, if you add areas which are not part of the cluster, that will not decrease the scientific value of the output. One more thing that I wanted to do is to make sure that the interface works with one finger. So you can add the line, you can modify the position, fine-tune it, and you can also delete by pulling the line to the other side from the clustering. The only thing that doesn't work with one finger is the zoom, because you still need to pinch, but that's very rare that you need the zoom to fine-tune your classification. One more thing, so it's not working in a way that every segmentation line cuts the whole image in two, but it creates a hierarchy of segmentation line. So the first line cuts the image in two, and then any subsequent lines that you add cuts that part in half, where you put your finger down. And then, of course, you can rearrange that. So if you take or drag the head of the line, which is marked by a small triangle, you can drag it to the other side, so you can very easily restructure your whole classification. And you see that very quickly you can create complex segmentation of images if it's needed. So based on all this, the whole workflow. First of all, you place your segmentation lines. Optionally, as I was mentioning, you can use zooming if you want to fine-tune. I personally played, I think, more than 1,000 tasks or 1,000 puzzles inside the desktop version, so I know quite well what it feels to play with Project Discovery. Usually you use 5, 6, 7 vertices to mark a polygon. Here you see that, and this is a relatively complex one because this is a 5-cluster sample. Super quickly you can put down those 4 lines and establish the initial structure. Now what I experience with this is that because it's so fast to put down these segmentation lines and so easy to manipulate them, you still have energy left to actually fine-tune your results before submitting. So you will see this is the second step when you're submitting the result. The puzzle zooms in, so you see, before you commit, you see what you're submitting, and you see that you can make quite a precise classification with these lines. And then, of course, we'll have the final step, which is going to be the reward screen. This is something that we're still working on. Surely it will show your scores. It will show how many analysis tokens you get for this classification. We'll have limits, as we have in the desktop version. We have daily limits for classifications. You will see that as well. And there will be a progression, so XP and ranks. This will be not connected, so this will be not synchronized with the EVE Online progression. It will be specific to the mobile app, and we'll still not decided 100% whether it will be per scientific minigame or an overarching progression in the mobile. So that's what I wanted to show you today. Please come to the booth. So we have mobile phones, you can give it a try. I mean, I try to explain it, but you really have to play with it yourself to see how intuitive this way of segmentation is. Please also subscribe to our newsletter. This is where we're going to communicate about where we are, if we have a beta testing, and so on. And lastly, together with the Zurich University of Applied Sciences, we're running a small research project. We got support from InnoSwiss, which is the Swiss innovation agency. And the goal of this research is to establish a fair and ethical monetization framework for the app. Now, I hope it goes without saying that the app will be, of course, free to download, free to play. I personally detest many ways of monetization that goes on in the mobile space. I don't think it would be, it would make any sense in the case of this app. It would contradict the philosophy, so we're not looking into anything that is disruptive or out of context. more like we want to understand if there's any way to have extra funding for the development. So if you can fill it in, that would be a huge help. And by the way, if you come to the booth and fill it in there, we can register your player account, and we have some special skins for that. So that's all for today. Thank you. Hope to see you at the booth.
I think we're going to change the slide deck now.
There is a PDF.
Well, while they do that, hi, I'm Ryan. I think we're good back there. What am I doing? Oh, it's up there. Good. We went too far already. Oh, I'm not seeing this. All right. I'm Dr. Ryan Brickman. I'm not a medical doctor. I'm a PhD. And I do this because I started my career because I want to save lives at scale. And that's why I started Project Discovery. And what I didn't realize is how it also changes people's lives. And I think that's the story I'm here to tell you today. It's really meaningful to me. I can try and get through this without crying. It's going to be hard. Sebastiano, you changed his life. He was a PhD student in my lab. This was his project. He's now a doctor himself, and this project was his work for 4 years. Leon Lee was an undergraduate student in my lab. He's here today. He's now getting his PhD. Project Discovery is part of his life as well. All these people change their lives, and I'll get a bit later about how it changed mine. Thank you, all you guys, for all the data that you gave us. It's an amazing story. And I'll tell you a bit what we did with all that. Not all of it was great. So we got kill marks. We had to get rid of some of the data to get that paper. Oh, this thing is a paper. It's out. We have it submitted for peer reviewed. So this is what we do as scientists. We make papers, we publish them. Right now it's under review. We got the reviews back. We hope to get it out. You can go look at it yourself and read what we did. I'm going to kind of go through it a bit more in detail now. We had to get some of the data. Triangles, it doesn't really fit for the data. We had a whole bunch of steps to get rid of some of the bad stuff. If there's only one polygon in the data, it looks like there's more, we got rid of that. And after we got rid of some of the easy stuff to get rid of, then we want to do is get the best players out there. So what we did is we recruited the candidates that had the highest number of polygons, and then at least 6 players had that same number. And then what we said is among those 6 players, they had to really agree on what that solution was. And we used something called the F1 score. And so in this plot on the left-hand side, if you assume that green box, the green rectangle on the left, is what one player said, and then that circle is what some other player said, and what they agreed on is those true positives. We had to have 6 people agree for that area where it's true positives, where everybody says that they had 90% or greater agreement among those dots. And then we said, this is probably a good solution. And those solutions went into our training data for the machine learning model that was developed in the lab, which I'll get to in a second. And what we did is we took those 6 solutions and we made a consensus out of them. So where did everybody agree is the center of all those, what is the group of cells in everybody's polygon? And we do that to increase availability, because if we put in like 50 million plots where everyone's all doing the same thing, it's not really good training data for machine learning algorithms or AI. So we wanted to have a really clean, consistent data set where there's consistent truth pattern, and to get rid of the individual bias, where it really doesn't matter if that one event is in or out by different players, just kind of get the consensus. That was our thought. We did that. And then it was a PhD stuff to take all that data and turn that into a machine learning algorithm. So this is what Sebastiano did for about 3 years, working through this all up. So he turned those numbers into plots. He used different kinds of models to figure out what the best one, random forest wins. We trained and validated different models. And then the flow magic algorithm was born. This is the result of his PhD algorithm. He developed a machine learning algorithm that can replicate what humans gate, what you guys gate, but without having to do all the work. So basically, we took all that data, and I think he finished a couple of years ago. We got it down to about 31,000 quality plots from about 839,000 players, and that was trained to use the model. and it worked. And so how do we know it worked? Because we took that machine learning gating algorithm that was trained on the plots that you gated, compared that to expert scientists and published papers who had done research. So what you see on the left-hand side is, now we're looking at how many cells are in the microliter of blood for different kinds of populations over days of life for human newborns and trying to see what's happening in the immune system after birth. So the left-hand side is a published paper, and it shows you that basically the counts, it's taking the counts and doing some math on it to how many cells in a microliter of blood. And then we had two different algorithms. One is a template model where the human expert draws one box around one plot in a whole series that they've collected on all these babies. Then we use that one gate to sort of throw it against as a bit of extra information against our training model, or our machine learning algorithm, and gate that all the rest of the data. And then we have a general purpose model that just says, just do your best job. And you can see the template model works really good. If you look at the first column on the left and the middle column, it looks pretty much the same. And mathematically, when we did the test, it's equivalent. And then we also tested on COVID data, COVID patients. Another paper that was published in the literature, the first left column is the reference, the middle column is a template model. When you line them up side by side, do the math, same exact results at the end. Fan-freaking-tastic. You guys are amazing. So then what we did is we released everything for anybody in the world, all that data to use for any purpose whatsoever, without any IP, without having to pay anybody money. Everybody could train their own models, because this is just a graduate student, right? And this was his life's work. There's smarter people out there than Sebastiano. Sebastiano, you're a great guy. There's other smart people out there that could maybe use that data to do other things. And we also gave away the code of his model so people can use that for any use whatsoever. And then I got thinking, well, if we did this in my lab where, just a bunch of, research people who don't really have any experience in ML, maybe could we do something better? And that's where my life changed. So I quit my job as a professor. I had a pretty good career, I didn't have to, it was a good life. But I thought we could do something better with that data. So I quit my job and joined a company called Dotmatics. Dotmatics was acquired by a very large corporation. You guys are all about corporations. It's a good one, called Siemens. It's a massive, massive company. And the idea is, what can we do with that same data to put it in the hands of scientists in the way that they can actually use? Because we're not in the business in academia of developing user interfaces or making software that is really usable. We need better people to do that. That's not an academic activity. We now have something developed in a software tool called OMIC. It's widely used by big pharma, by research scientists to analyze flow cytometry data. It's an amazing piece of software. But in that tool, they get plots like this, and then they have to use their mouse, the scientists, to gate that data. What we've been able to do that is give them, we've been working on this for about 3 years now. We're about to release it. They tell me really soon now. It should be out in a couple of weeks. We have our own little conference coming out, a big flow cytometry conference. We hope to announce it there, where we can show them. You just push a button to gate the data. So this is an example problem. So here's, on the left-hand side, are example real data that people are trying to gate to solve disease. What we say is, give us one solution on one example data from this data set. And you can see the data set, it's all kind of looking at the same kind of people for the same kind of data. So give us one example. We're going to try to use that one example to gate those other three on the left. Now, if you just took that one gate on that top left and sort of pasted it across all the other samples, it doesn't work, right? Because the data moves around. That's the whole problem in our science. But with this adaptive gate model that we've developed commercially based on that same data, it works. It works so good that we're going to put this in a commercial tool, put this in the hand of scientists so they can use this for all the different diseases that flow cytometry is important for, and for research. It doesn't suck. It's as good as the humans can do, which is why we're willing to put that in front of the humans, because we don't want to look bad as a company, right? And then you changed a bunch of more lives, and this is where it gets really interesting. So we started with COVID. You've been looking at cancer. Now what we're going to do with the data that you're looking at is we're going to discover what truth is. And the whole problem that we have, or one of the problems that we have in flow cytometry is when we put the problem I came to is when I saw what this algorithm is doing in our software tool, The software tool doesn't know what these populations are, right? We can draw those boxes, but what's important to science is we have names for things. This is how we talk about science. And when the algorithm popped them out, it just says, like, it gave them random names, like 2ZFY or 3ZFX7. The only thing we did by solving the gating problem is move the problem down to the next step in the pathway, which is you've discovered these cells, or you've identified them. What cells are they? And you have to put the names on them so we can talk about them in the literature. And, well, can we automate that task as well? And it turns out we can't. Because the problem is the definition of what defines a population. Well, what defines the population is where it is in that plot. So it's in this space, so we know what it is, and that allows us to give it a name. The problem is scientists suck, because the way that not only do we have a problem that how they draw the gates around it is highly variable because it's human-driven, the terms they use to describe those cells are a mess. So here's a bunch of examples. So what I did is I went to Google and I said, looking at these two markers, CD16 versus CD56, show me all the plots where people have analyzed that. You can see all the scientists are gating it in different ways, and the labels that they're using are all different. It's a mess. So here's one example here. You can see this scientist has called it CD16 negative, CD56 high. It's negative because it's on this side, it's high because it's up here. This other person has gated it differently, but they've called it bright. This person's called it dim. And so computationally, so my background is computational biology, doing things at scale. This doesn't scale. We can't put labels on this because people are calling it different. And the computers don't understand the difference between what a high is versus a bright, or a positive versus negative. The terminology isn't consistent. It's like if you went to a doctor and one doctor calls it a femur and somebody else calls it a cow, right? You just can't exchange knowledge between people. And that's a problem for science. So what we really want to do is have data being globally findable, being interoperable, being reusable. This is something we talk about in science law, having fair data. Flow cytometry data isn't fair because we can't find it because we don't know the terms that people used. That's the next problem. And we're going to solve this because of you. So what I did is I started something called SOULCAP. And this is going to be the way that we're going to standardize the terminology for scientists around the world for how to describe flow cytometry data. A standardized nomenclature, reference maps, benchmark data sets, gating algorithms, reference labeling implementations, all these different things. I thought it was just a bioinformatics problem. It turned out to be I just wanted to put labels on these plots. Turned out we have to solve a lot of other problems at the same time. So what I did is, inspired by all you guys, I went and socialized this idea to all the flow cytometry people. I've been around for a while. And people understand that this is a problem. Scientists understand this is a problem. This is the first meeting we had at a flow cytometry meeting called CITO. And these are the people who are involved in SOULCAP. These people are all key opinion leaders and subject matter experts in flow cytometry who are volunteering their time to get the labeling right, based off the data that you guys are analyzing now. So what the first thing we're doing is we're trying to come up with how do we find these populations? What are the reagents that we use to define them? Because we can use different kinds of, and we won't talk about this in a lot of the learning material you've seen, but what are the reagents that we have to use to define them? What are the axes going to be? And we want to standardize that first so that we kind of say, if you want to call this a T cell, that you have to use these markers. And the community understands that we have to do that because we have to standardize the terminology. In order to understand the terminology, we have to standardize how we do the experiments. And the next step is we then tie the words. So if you just write this letter called NK cells, for natural killer cells, that's just a bunch of letters that don't really mean anything. But as humans, we have this idea in our head for what that function actually means. The next thing we have to do is make that in a way that computers can program on that. And that's where ontologies come in. Ontologies are computational ways to describe knowledge. And so what we're going to do is we're going to tie the term, like NK cells for the label of those populations, into a computationally tractable tool that software can compute on. And that's going to be amazing. And then we can develop benchmark data sets. And we've done this before, so that we can ascertain the performance of different algorithms like the one that we developed and other people can develop on the SOULCAP data to make sure that they're performant is at least as good as humans. Leon is here today, and he's right now, he came out of my lab, he's now working on this project to be able to transfer the labels from our reference maps that we're developing in SOULCAP to data from the scientists. This data that we're training on is data that you're analyzing today, like right freaking now. So, because he's got a conference in about 4 weeks, and he wants to go up there on stage and talk about that. Hurry up, guys. And not only is this going to solve in our domain of flow cytometry, because we're using ontologies, we're not the only people looking at cells. There's other technologies out there that are also looking at the same cells using different techniques. Single-cell transcriptomics, multiplex immunofluorescence, spatial transcriptomics. All those other scientific fields are also using these words like NK cells. We can use the ontology to tie between these different technologies so that we can layer more data types together along with the flow cytometry data. NIST is involved. NIST is the National Institute for Standard Technology in the USA. They set federal guidelines for standards. We're collaborating with them, and they have all the instrument vendors who make the flow cytometry machines in the world working with NIST, and we're bringing our SOULCAP effort with them to put this in the hands of the vendors who make the instruments, as well as the vendors who make the software. So we have all these committees now. Education, the standard that comes off the machines, the FCS standard, how to qualify the reagents, how to validate in software that things are working the way they're supposed to, how to validate and build the reagents that people use. We have expert panels. How we're going to do this, we're going to put all the scientists who understand T cells in the room and get them to agree through a rigorous process that, yes, this is how we're going to describe the language that we do the science. Probably not everybody's going to agree, but what we're going to say is, if 80% of the people agree, we'll stop there, and then at one point our agreement's going to stop, but can we at least get some consensus for most of the important populations out there and start there so that any automated gating tool that anybody can use the idea, and it's our software or somebody else's software, there that everybody else has agreed to, and that's going to change the science. And that's going to change the science because that's going to allow us to leverage AI. And this is where it gets really cool, because we have the technology right now that in the labs, we can take the data off the machine and stream it into software. Then we can automatically gate the software with tools that we or other people develop. Then we can automatically label things in a consistent way. Then we can do statistics on that just a pipeline passing it through, and then we can put plots in front of the scientists that says, we've got the data, we've gated it, we've labeled it, we've automatically done the statistics because we know what you're looking for. Then all the scientist has to go and says, oh, here's a whole bunch of plots, this one looks different, and this patient has acted differently than all these other patients. You've done all this work for me. I don't have to do that gating anymore. I just look at this. I say, oh, what's going on here? This one's interesting. What's happening here? We've streamlined the science. Not only that, when we have this in place, we can go back to all the data that's ever been collected. Because pharma doesn't throw out their data. They keep it all, right? What if, and all the data they've collected has been done by different people in different labs with different ways to gate the data. They put different labels on that. Now, with these automated tools, we can go back, reanalyze, reannotate, and then what if in this drug something happened, in this drug something different happened? That's going to be amazing, because that data is just sitting there. Now, it's good for my company, because we can go in like, how much would you pay for that? Good for us, but it's good for science, because we're going to unlock all that data just sitting around. Not only going forward, but going back in time. And I believe this is going to happen, and I'm up here to put my name on that. So I have a lot of people to thank. Mostly I have to thank my boss, Brett. Thank you for letting me do whatever I want to do. We have all the different societies behind this project. These societies represent thousands and thousands and thousands of scientists. When I started this idea, I went to them saying, if we build it, will you sign off on that? And when they said yes, I knew we could do this. We have an independent board of directors. It's a not-for-profit company that I set up, so it's outside of Dotmatic, so it's just to make it clean. On that board of directors, we have amazing people. We have the president of one of these societies. We have Mario Roederer, who was the leader of the NIH flow cytometry core. These are key opinion leaders. We have different groups. These people, Kelly Lunston, Sophie Van Gassen, Camila, are leaders in the field who are all handling different parts of this project. And it's all because of you guys. You guys are going to change the world. You're going to save lives at scale. Thank you very much. Happy to answer me, and I guess everybody else here will be happy to answer any questions. It covers, it's basically all the different cell types. And we're working.
5 megabytes or like 5 terabytes?
It's megabytes. It's not that big, but it's the knowledge that's inscribed in it. It's a directed acyclic graph. If you want to geek out on stuff.
Does it use OWL?
Yes.
Yeah. Okay. Cool.
Yeah.
I've been playing around with ontologies for a while.
Yeah. So the cell ontology has been around for a long time, and they are collaborating on this project. And they want they're going to put all our terms into their ontology with SOULCAP labels, and it is widely used by everybody.
So there's a big thing in the AI world about collapsing your contexts, and I feel like ontologies are like super dense contexts, so that you can use cheap AI.
Yep.
To do AI on it.
It's super duper. I can totally geek out with you on that all day. Everybody else, it's really cool science. Right back there, I think.
So, no, it's up here. Hi.
Hi, wherever you are.
So just a question. When you say it's been helpful, is there like, can you quantify that? So, did we cure cancer in a meaningful way already, or?
No. When I say
it
will be helpful. So we're developing these tools now. We're putting them in the hands of scientists now. So we haven't cured cancer yet, but all this is building the tools are going to be, the tools are there that allow us to put that in the hands of scientists.
Right. But with the previous projects?
The previous project, that was showing that these tools what we've done is show that these tools can work to replicate what was done before. If we had those tools originally, we could have not had to do the work that the scientists had to do, which gives us the confidence that we can now do it for other things.
Yeah. Okay, thank you.
Hi, my question is about the mobile app, which looks really good, by the way. That looks like really intuitive to use. What's stopping the syncing with an EVE Online account? Because I think that's going to be a really essential feature for engagement when there's like progression tied to your account and all of that.
So, well, first of all, you can use your EVE login to log into the mobile app. Moreover, you have to log in if you want to exchange the analysis tokens to rewards. We want to create some connections, so I'm always thinking about like whether you can bring over some of your corporation data, make groups in the mobile app. These are extra features that we're trying to implement. There will be no synchronization of your progression. There will be no synchronization of your accuracy score, partly because how the mobile works is there will be different scientific mini games in the future, and so there will be let's say the flagship project, EVE Online, but all the rest will only be in the mobile. For things inside EVE, and we had a discussion yesterday at CCP, and it seems that CCP can even support that you can have some individual portfolio of rewards based on your account ID. So yeah, we're thinking along these lines. We don't want to. So one of the reasons we started to think about creating this mobile app is that what I learned in the last 10 years is that asking game developer companies to create something in the game, it's a huge ask. Like, they're super swamped. So it's really, in retrospect, it's a miracle that we managed to pull this off with CCP. Like, I talked to hundreds of game developers. Everybody is super excited. They're inspired by this. They don't have the luxuries to set aside a team. So the idea is to put as small amount of work on CCP side as possible. So we want to do as much inside the mobile app when it comes to development as possible.
Hello, this is a question for Ryan or Attila. So dealing with all this disparate data from NIH, NHS, NIST, how are you collaborating? How are you organizing that data? How are you handling the biased, non-biased results maybe, and coming together on an agreeable point of references for what you're doing?
Great question. So the question is, how are we going to get around all that mess of data? We're doing it ourselves. So we have this team of experts who's going to, what we're doing is redoing all the experiments based on going to the literature first, saying, where are we? What do we understand? And then doing the experiments in the wet lab to develop the true standard. So if, for example, part of it has been historical, that the machines that we've used didn't have the ability to look at everything, and so people were lazy and didn't run enough markers, and didn't have enough data. So the idea that we have in our head is, what is the minimum number of essential markers to define something that is pure? And that's a question that was never really asked before, and that is going to be our building blocks, is doing the experiments in the wet lab. And what people have done is, large vendors of reagents, people with instruments, have come forward and giving us the reagents to do all that work. To start again, clean slate. If we want to do this right from the beginning, we're doing the experiments to get that truth data. And it's a bit of work. But volunteers are willing to do that effort. We have experts from AbbVie, from all these big pharma, who are volunteering their time because all the big pharma companies want to get to that truth, because that's going to help them generate the data that they can then analyze. Or actually, you guys. And again, all that is going to be given away for any use whatsoever without anybody paying for it. And that's why we're all here. So thank you very much for that, guys. We good? Keep it up, because it is going to, like I said, it's really going to save lives at scale, and I see it. Other people do too. People are putting a lot of time, a lot of effort to taking that work that you're doing and making something promising to save lives. Thank you.